In the video Quadric Surfaces 1, we saw the general quadratic equation in variables x, y, z. It's got 10 terms and it looks like this. That we call a set of points x, y, z that satisfies a quadratic equation like that a quadric surface. And we're wondering, what kind of quadric surfaces can you get? Well, that equation is pretty general because it describes any quadric surface situated anywhere and oriented in any direction. If you imagine a surface, you want to kind of pull it right in front of you, say, like center it at the origin, and maybe you want to orient it in a nice way. So, for example, orient it along one of the axes. Without bending or stretching the surface, just pick it up and move it so that it sits right in front of you. We can achieve this by, translating and rotating. And then we get equations like this. These are what you might call standard forms. And we saw in Quadric Surfaces 1 that you can get cylinders. I don't mean cylinder in the usual sense of the term, but a cylinder being a curve in a plane that is then stretched out along an axis perpendicular to the plane. So cylinders you get. What else can you get? So here's what we're going to do to make our investigation a little bit simpler. Let's imagine that we can expand or contract along coordinate axes. So, for example, if you started with the equation of an ellipse, which we'll see here in a moment, maybe it looks like this. Let's take x over 2 all squared. There we go. Let's just introduce new variables, u, v, and w, to be x over 2, y, z over 3, and then the equation takes the form u squared plus v squared plus w squared equals 1. So if we give ourselves the freedom to do this in this way, just to get a feel for the different types of surfaces that are out there, quadric surfaces, it's enough to just consider these coefficients, a, b, I, c, and j, to be plus or minus 1 or 0. And we could get any other values by stretching the coordinate axes. Now, let's go. Here, for example, is an ellipsoid, just rotated there. It might be helpful to review the method of taking slices or traces to visualize a surface. So there is a horizontal slice of the ellipsoid. There's a vertical slice in red. And here is another vertical slice in purple, being ellipsoid, circle, and ellipsoid respectively. That's covered in some detail in Quadric Surfaces 1. All right, now let's start with this first equation of the standard forms. ax squared plus by squared plus iz is 0. We'll start by assuming I is 0, and then we just get an equation involving x and y. It doesn't depend on z. So this is, here, let's look at the cases. You can have x squared plus y squared is 0. That just has the single point, the origin, as a solution. You can have x squared minus y squared is 0, and that'll give two intersecting lines like this. You can take minus 1 and plus 1 for the coefficients, but that'll just give the same as the previous case. If you take two minus 1s for coefficients, that'll give the same solution set as the first. And if you want to take it further and you want to let, say, a or b be 0, let's let a be 1 and b be 0. You get x squared equals 0. The set of points satisfying that equation is just the y-axis. Now those are the graphs in the xy plane, but to graph the surface we have to stretch these out along the z-axis. So there's one. Here's the next one. It's two intersecting planes, those two lines stretched out along the z-axis. Two intersecting planes. Here's a maple picture of it. We'll just overlay this here, rotate it around just to get an idea. Now these are what you might call cylinders. Generalized cylinders. They're sets of points in the xy plane that are then stretched out along, in these cases, the z-axis. We're going to stop considering these what you might call degenerate cases. We want to study curved surfaces. So let's move on here, and now we'll assume that I is not 0. Then what are the possibilities here? Well, you can take, by rescaling, you can assume that I is minus 1. So then you'd have z equals ax squared plus by squared. And let's just work through the possibilities. If a and b are both plus 1, you get a paraboloid. This is covered in some detail in the video Quadric Surfaces 1, how to get that picture there. If z equals minus x squared minus y squared, so take two minus ones, well, then you just get the negative of the previous picture, so the bowl flipped upside down. These are both paraboloids. Their horizontal traces are circles, and their vertical traces are parabolas. Let's take 1 and minus 1 for coefficients now. What we get? Here we actually get a saddle shape. Again, this is covered in some detail in Quadric Surfaces 1. And if you take minus 1 and 1 for coefficients, you again get a kind of a saddle shape here, just oriented differently. These are what are called hyperbolic paraboloids, and the horizontal traces now are hyperbolas, and the vertical traces are parabolas. Okay, very nice so far. Let's move on to the next equation here. Ax squared plus by squared plus cz plus j equals 0. We'll examine the possibilities thoroughly here. Let's start by assuming that a and b and c are all not 0. Because if one of them is 0, then the corresponding variable doesn't enter in. You're back in that generalized cylinder kind of situation. First of all, if j is 0, then the first possibility, x squared plus y squared plus z squared equals 0, gives just the origin. The next case here, if you take a to be plus 1, b to be plus 1, and c to be minus 1, you can rewrite that as x squared plus y squared equals z squared. And here you will get a cone. Horizontal traces will be circles, and we'll talk about vertical traces in a moment here. If you take the negative 1 to be in front of y squared, you get a cone oriented along the y-axis. If the negative goes in front of the x squared, you get a cone along the x-axis. So some of these traces are circles, and other traces are hyperbolas, provided we take traces parallel to the coordinate axes. Okay, we'll keep going here, assuming j is not 0. And then again, by rescaling, we can assume that j is minus 1. So we have this equation. The first case here, taking all plus 1s, gives the equation of a sphere. X squared plus y squared minus z squared equals 1. Well, here the horizontal traces are going to be circles, and the vertical traces are hyperbolas. I'm light on details here. This is just to give a quick understanding of the types of surfaces. This is called a hyperboloid of one sheet. There's a picture using maple. And notice that the negative corresponds with the axis of symmetry. So if you put the negative sign in front of the y squared, you get a hyperboloid of one sheet along the y-axis. If the negative goes in front of the x squared, you'll get a hyperboloid of one sheet along the x-axis. Okay, now let's keep going. Now, those three cases involved two positive ones and one negative one. What if we take two negatives and one positive? Well, now, picture the horizontal traces. These are obtained by taking z equal to k. So if you plug in z equal to k there, you can get the equation by rearranging x squared plus y squared equals k squared minus 1. Now those describe circles provided that k squared minus 1 is positive. So k is greater than 1 or k is less than minus 1. So it actually gives two sheets here. Horizontal traces are circles and vertical traces are hyperbolas crossing the z-axis. This is a hyperboloid of two sheets. Again, there's a picture drawn using maple. Notice that the plus sign this time corresponds to the axis of symmetry. So if you put the plus 1 in front of y squared, you get a hyperboloid of two sheets along the y-axis. If the plus sign goes in front of x squared, you get a hyperboloid of two sheets oriented along the x-axis. Lastly, if you take all negative 1s, well, this has no real solution. So here you'd be in the domain of complex solution sets. That'd be interesting. We'll leave that for another time. So that's a fairly exhaustive treatment of the basic types of quadric surfaces that you can get with these coefficients of plus or minus 1 and 0. You can get more general ones by translating. So for example, here's a hyperboloid of one sheet oriented along the y-axis, shifted along the x-axis by 1. You can rescale. So for example, this is going to give you an ellipsoid stretched along the x-axis by a factor of 2. You can rotate as well. So for example, here's a hyperboloid of 2 sheets rotated a bit. That's just a little bit trickier. Not much, just a little bit, and it requires some linear algebra, some knowledge of more general types of linear transformations. That's fun. Now, let's bring all this back home to conic sections. Now that we've seen the equation of a cone, there it is, this particular cone, and let's consider a general plane, z equals ax plus by plus c. And let's intersect the two. That's how we get conic sections. So let's take the equation of the plane and square it. So we get z squared equals that stuff squared, and we'll expand it out to get a bunch of stuff. Now, if that general plane there is going to intersect that particular cone, that also has to be equal to x squared plus y squared. So if you rearrange, you can write the equation in this form with coefficients capital A, B, C, D, E, F, where A, B, C, D, E, F are given in terms of little a, b, c, like this. And that equation there is what we see as the general quadratic in variables x and y, and that's what generated our discussion of conic sections in the video Conic Sections 1. Maybe you've seen it, maybe you haven't. If you haven't, I'd urge you to watch it. In any case, thanks for watching.